In this video, we look at double angle formulae. Now, if an angle is multiplied by 2, we consider it a double angle. And we have special formulae for sine of a double angle and cos of a double angle. And they are sine 2 theta equals 2 sine theta cos theta. And the cos double angle formulae goes to 3 different options. Cos theta all squared minus sine theta all squared, or 2 cos theta all squared minus 1, or 1 minus 2 sine theta all squared. Now I'm quickly going to look at where these formulae come from. So if we look at the sine double angle formula, we can consider that sine 2 theta is the same as theta plus theta, which is a compound angle. Now, from the sine compound angle formula, we know that this expands to sine theta cos theta plus, keeping the same plus there, cos theta sine theta. Now, if we look at our two terms, they are like terms because I have the exact same trig functions and the exact same angles. So even though the first term has sine cos, and the second term has cos first and then sine, it doesn't matter the order in which I multiply the trig functions there. Okay, so they are exactly the same like terms. So I'm adding 2 of the same term. So this gives me 2 sine theta cos theta, which is our double angle formula. If we then look at the cos double angle, okay, it gives us 3 options. So if we consider the first one, and we consider the fact that cos 2 theta is the same as cos theta plus theta, again it gives us a compound angle, okay? And we know that a cos compound angle expands as cos theta, and then we change the sign from plus to a minus, and then we have sine of the angle, okay? Now this simplifies to cos theta times cos theta is cos theta all squared, minus sine theta times sine theta is sine theta all squared, which gives us our first option there. Okay, now if we substitute one of these from part of the square identity, we get the other 2 options. Okay, so let's quickly recap the square identity. Okay, so I have sine theta squared plus cos theta all squared equals 1. If I were to take the square identity and solve it for cos theta squared, I would subtract sine theta squared from both sides, and I'd have that cos theta squared is equal to 1 minus sine theta all squared. If I wanted to solve it for sine theta squared, I would then subtract the cos theta squared from both sides, and I'd get that sine theta all squared is equal to 1 minus cos theta all squared. Okay, so if I take this first form of the cos double angle formula, if I were to substitute one of these with its equivalent from the square identity, I get the other 2 options. So cos theta squared is equal to 1 minus sine theta all squared, and then I complete the expanded form there, and this simplifies to 1 minus 2 sine theta all squared, which was our last option here. Okay, again, if I were to take the cos theta squared minus sine theta squared, and in this case choose to replace the sine theta squared with its equivalent from the square identity, I would get that this is equal to cos theta all squared minus, now sine theta all squared is equal to 1 minus cos theta all squared. This simplifies to cos theta squared minus 1 plus cos theta squared. Adding like terms, that gives me 2 cos theta squareds minus 1, which is our third option there. Okay, now what we are going to do is look at examples of how to use the double angle formulae. So we can either expand, so that's working from left to right in the formula, or contract, so that's when we work from the right to the left. So in this first example, we are going to expand, and the instruction is to expand the following using double angle formulae. And just to help us out here, I have summarized the formulae in our little pink box here. So if we look at the first one, I have sine 2x. So I am doubling the angle x, and it is a sine double angle, so I would expand it according to the formula. Okay, so expanding, I go from left to right. So I have 2 sine, and then the angle that is being doubled, which is x, then cos the x again. Okay, and that's it. If I go to the second question, it says sine 50 degrees. Okay, now what is being doubled to give us 50? That would be 25. So 25 degrees is being doubled to give us the 50. Okay, so again, if I expand, I go from left to right, and the sine double angle formula says it's equal to 2 times sine of half the angle, so it's 25 degrees, times cos of half the angle, which is 25 degrees, and that is the expanded form. Okay, if we look at number 3, cos A, we have to expand this. We're told to expand this using the double angle formula. Okay, so I have cos, I've got 3 options, but I need to understand what is being doubled. Okay, so I have cos 2 times what would give me A. That would be a half A, okay, which I can also write as A over 2. So if you see, if we were to multiply this, those 2's would cancel and we'd be left with the initial A. Okay, now I have 3 options of how to expand this. Okay, if I go according to the first option, this would expand to cos half the angle, which is A over 2 squared, and then minus sine half the angle, which is A over 2 squared. Okay, if I were to choose to expand it according to the second version, okay, that would go to 2 cos of the angle, which is A over 2 squared, minus 1. The third option would be 1 minus 2 sine of the angle, or half the angle, which is A over 2 squared, and that would be the third option. Okay, now we are asked to contract, which means we are going to be working from the right side of the formula to the left side. Okay, so if we look at the first one, so it says write as a trigonometric ratio of a single angle. Okay, so I have 2 sine A over 2 cos A over 2. The first thing I notice is that my angles are the same, which is good. I need them to be the same to use the formulae. Okay, then I see that I have 2 and then a sine and a cos multiplied to each other. The only formula with sine and cos multiplied to each other is the sine double angle formula. Okay, so I'm going to contract, so I'm working from right to left. Okay, so I know that this will equal sine 2 times, now what's the angle? It is A over 2, and that simplifies to the 2's cancel, and I have sine A. Okay, if we look at number 2, we have sine theta times cos theta. Now the only double angle formula with sine times cos, so where they are multiplied to each other, is the sine double angle formula. The problem though is that I don't have this 2. Okay, I have the sine theta times the cos theta, but I don't have that 2. But in order to use the double angle formula, I need that 2. So let's see, if I were to put in the 2, okay, I'm obviously changing the value of the expression, which means that this cannot be equal. So what would I have to do to make them equal? Okay, I can multiply it by a half. Okay, a half times 2 is 1. 1 is the coefficient initially, so that means I'm not changing the value. But what I do now have is a full double angle formula on the right hand side there. So 2 sine theta cos theta, going from right to left, contracts to sine 2 theta, and that is my final answer. Right, a third question where we have to contract. It says right is a trigonometric ratio of a single angle. Okay, now if we look at it, it says 2 minus 4 sine theta all squared. Okay, now looking at the double angle formulae, the only case where I have sine theta squared being the only trig function in the formula is this last option for the cos double angle formula. Okay, but if we look there, here I have 1 minus 2 sine theta squared. Here I don't have the 1 and 2, I've got 2 and 4. Okay, but I notice that I have a common factor. So this question requires a bit of manipulation. Okay, so we have to factorize out the 2. And if I factorize out the 2, I'm left with 1 minus 2 sine theta all squared. Okay, and that is exactly the last option for the cos double angle. So we know that moving from right to left, it contracts to cos 2 times the angle, which was theta. Okay. A fourth example of contracting. Again, right is a trigonometric ratio of a single angle, and we have 3 minus 6 cos p all squared. Okay. Looking at our double angle formulae, the only formula that has cos theta squared being the only trig function is this option for the cos double angle formula. Okay. But what we notice in the formula is that the cos of the angle squared comes first and it's positive. Okay, it's a positive term. And then we subtract 1. So that's not yet quite what we have here. Okay. What I do notice is that my two terms, 3 minus 6 cos p all squared, have a common factor of 3. So I'm going to factorize out the 3. Okay, and I'm left with 1 minus 2 cos p all squared. Okay, I'm getting closer to the double angle formula. So I have the 1 minus and then the 2 cos p all squared. But in the formula, the cos of the angle squared is positive. So in order to make this positive, I need to factorize out a further negative 1. Okay, so this is going to become negative 3. My 1 is going to become negative 1, and I'm going to write it as a second term in my brackets. And the negative 2 cos p all squared is going to become positive 2 cos p all squared. Okay, now what I have in the bracket is what I have in the double angle formula, and I know that moving from right to left, I can contract it. Okay, so I'm left with negative 3 and then cos and the double angle. Okay, sorry, this is a fifth example. Right, now it says write as a trigonometric ratio of a single acute angle. So we have to remember this, okay, because it's different. Now if I look at this, I have sine 130 degrees times sine of 140 degrees, okay. Comparing this to the double angle formula, I have no formula with a sine times a sine trig function. Okay, so we have to do a bit of manipulation. Now, I cannot factorize out anything, but what I do have in my toolbox is I can reduce these angles. Okay, so if I reduce two acute angles, okay, and keeping in mind that I want a double angle formula to be applicable, okay, I ideally would like to change one of these to cos, okay. So I'm looking for a situation where I can have a sine of an angle times cos of an angle, and that angle being the same. Okay, so if I look at sine 130 degrees, I see that since 130 degrees is in the second quadrant, we can rewrite 130 as 180 degrees minus 50 degrees. Okay. Sine of 140 degrees. 140 again is in the second quadrant. So I could write it as sine of 180 degrees minus 40 degrees, but that would reduce to an angle that's different to the first trig function here. The other option I have is to write 140 as 90 degrees plus 50. Okay, so sine of 90 degrees plus 50. Okay, the usefulness of this to me is that I would end up reducing to the same angle, and the 90 degrees would make this go to its co-function, which is cos, which is exactly what I need. Okay, so reducing this, sine in the second quadrant is positive, so this reduces to positive sine 50 degrees times sine in the second quadrant is positive again, but this reduces to the co-function cos 50. Okay, so now I have sine times a cos, okay, of an angle. I still am missing the 2, and as in the previous example, we've seen that I can add that to, I can write it in, okay, sorry, that's 50 degrees times cos 50 degrees, but I must just remember that I'm changing the value, so I have to keep the value by multiplying by a half. Okay, so this now is my double angle, and I can contract it moving from right to left. So I have a half times sine of double the angle. Okay, so that gives me a half of sine 100 degrees. Okay, now the instructions said write as a trig ratio of a single acute angle. Now, an acute angle is an angle that's less than 90 degrees. This is not an acute angle, so I have to reduce it. So I have a half times sine. I can rewrite 100 as 180 degrees minus 80. Okay, so that would then reduce to sine 80 degrees. So my final answer is a half sine 80 degrees. Okay, then we have a third type of question which involves the use of our special angles. Okay, so calculate without a calculator, and we have 2 sine 15 cos 15. Now if you look carefully at the double angle formulae, that is our sine double angle formula. Okay, so this contracts to sine 2 times the angle, which is 15 degrees, and that gives us sine 30 degrees. And if you remember your special angles, sine of 30 degrees is equal to a half. Okay, then again calculate without a calculator, and we have 1 minus 2 cos 22,5 degrees all squared. Okay, now if we compare the double angle formulae, I am seeing a similarity to this formula, okay? But the problem is that my cos angle or squared term must be positive. So that means I need to factorize out a -1. That leaves me with this positive 1 becoming -1, and I'm going to write it as a second term. And the -2 cos 22,5 degrees all squared term will become positive. Okay, now what I have in the brackets is the form of the cos double angle formulae that I had underlined here. So I know that it contracts from right to left as cos double the angle, which in this case is 22,5 degrees. Now 2 times 22,5 degrees is 45 degrees. And 45 degrees is a special angle whose value is root 2 over 2. Final example, we have cos 15 degrees plus sine 15 degrees all squared. Okay, so the all squared means I am squaring that bracket by itself twice. Okay, and I can use FOIL to multiply this out. So the firsts give me cos 15 degrees all squared. The outers give me cos 15 times sine 15. The inners give me sine 15 times cos 15 degrees. Now those are like terms. So I'm going to end up with 2 sine 15 degrees times cos 15 degrees. Okay. And then the lasts give me sine 15 degrees all squared. Okay. Now I'm just going to rewrite this order to show you something. So I'm going to write the cos 15 degrees all squared first, and then the sine 15 degrees squared second, and then the 2 sine 15 degrees cos 15 degrees. Now if you look at this, this is the square identity. Okay. Remember, if I have cos x squared plus sine x all squared, it is equal to 1. So the value of this is 1. And what I have here in the last term is my sine double angle, which I can contract. So this is equal to 1 plus, this contracts to sine of 2 times the angle, which is 15 degrees. Now sine 2 times 15 is sine of 30 degrees, which is a special angle. Sine of 30 is a half, and this simplifies to 1.5 or 3/2.